If you click this video away, please tell me what it was so that I can may improve. Otherwise, hi and welcome. I am trying to learn physics. Today, how light behaves, and after we've done it, we're going to do body center training. And if you participate in the body center training, then it's been at your own risk. How light behaves, the visible part of a broad spectrum of radiated energy. Okay, the thing is that we are saying already that there is different types of radiated energy, and light is the thing basically which can be seen of all this radiation energy. Light plays a unique part in science. To begin with, it makes seeing possible, and visual observation is one of the main ways of gathering information about the universe. In addition, the speed of light in free space is one of the fundamental physical constants of the universe. Okay, the speed of light is a constant of the universe. That means everywhere in the universe, light has the same speed, with 300,000 kilometers per second. It is the same at all times for all people in all places. And unlike other speeds, it remains unaltered however fast the observer may be moving. This simple fact underlies the whole of modern physics, for it governs the way of the universe behaves. Okay, the controversy over the actual nature of light, whether it consists of particles or waves, involved some of the best known experiments in the history of science. Okay, here at that place I'm going to say this book is from 1978. Maybe there's more found out. Okay, wave, they are saying light is moving. There's a controversy in 1978 about whether light moves as a wave or as consistent. Whether it are particles or moves as a wave. The forming of colors. Any theory about the nature of light has to take into account a number of basic properties of light and the way it interacts with matter. Okay, we have to have clear what light is, and one part of it is to find out whether it consists out of particles, consistent particles, or a wave. These interactions are responsible for the way an object appears to the eye, including its color. Okay, color is an important aspect. We try to find out what we are telling here, and we try to find out what light is. And the color of the light is also important for the eye. The first real understanding of color came from an experiment carried out by the English mathematician Sir Isaac Newton in 1666. Newton passed a beam of light through a prism and found that it was split up into a series of colors. The spectrum of colors of the rainbow, with red being refracted or bent least, and violet being refracted most. Okay, first a prism. I don't think we have it here. That I think that is like a triangle. So the light comes in, but then it cannot go straight through it because it's triangular, and so it has to go to the sides like that, out and out. And therefore the light comes in and is now split in different layers, different spectrums, and you can see the red, green, blue, whatever. And there was said refracted or bent, least and violet being refracted most. I don't really understand that part. Reversing the experiment, the colors could be recombined to give white light. Okay, I don't know exactly how, maybe we're going to explain it. But I think he was first splitting it into a red, a blue and a green one, and then he was taking there exactly the red light beam, put another prism there, and bent it again down into one, and another prism here, and all together in one, and then the light was again white. So all these colors, after having been split up and fused again together, had again the color of light, white, or invisible. This experiment showed that whiteness is the result of a combination of many different colors. Okay, there's no said all colors together are giving white. It also suggested why it is that different objects have different colors. They absorb or reflect different parts of a spectrum. Okay, they said that some things are reflecting other other amounts or other types of colors and are reflecting other types of colors. That means that this book is reflecting here another part of color than here. This material is reflecting differently, and that gives it the color. So the light is just coming onto it, but the thing out of which this consists absorbs some types of colors, maybe all the red parts and all the blue parts, and at the end we have some green, whatever it is, because that is the only part which is reflected. Thus, a blue object absorbs the red, yellow and green parts of white light and reflects the blue part. Okay, if something is blue, like this bookmark, that means all the white light with all its 5 colors or whatever comes into it, and the red goes just on, it is coming into it, and the green and the yellow, but the blue part comes again out. And I think that is because they have different wavelengths, I think. But maybe we're going to explain it. I don't know, so forget it. An object in the path of a beam of light can cast a sharp shadow. This immediately lends support to the notion of light as rays traveling in straight lines from the source. Okay, they're saying that things making a shadow. So there, now we have any shadow. So the idea is the light comes in a straight line, and now we have a shadow. It makes sense. Newton thought of light as a stream of small luminous particles or corpuscles with a different sort of corpuscle for each color. I think he meant what light were some particles go, and they had different sizes, and that made them having different colors. The theory worked reasonably well as an explanation of the observable properties of light, but there were several drawbacks. Okay, Newton's idea was quite good, but not perfect. For one thing, Newton's explanation of refraction required that light should travel faster in a dense medium such as water than in a less dense medium such as air. This is certainly not the case. I don't understand what we mean with it, why that Newton's thing would require it. Maybe because they had different sizes and they would be slower, whatever. This is certainly not the case. Light seems to travel everywhere the same speed, whether it's in water or not. There was also the fact that shadows, when examined carefully, are less than absolutely sharp. There is some light just inside the geometrical shadow, and some faint dark lines, known as diffraction fringes, just outside. What we're saying here is something which has a shadow, but the shadow is not completely exactly. It has a little overgoing to the side. And even if it is a complete, perfectly edge, they're saying that if it would go completely, it would make a complete, perfect shadow. But some light seems to go left or right. And the explanation for that would be wavelength behavior. So the light comes not straight, but more in a wave. Then it can go a bit to the other side. An alternative theory of light was expounded in 1678 by the Dutch physicist Christian Huygens. Okay, another person, Christian Huygens. He suggested that light was a form of wave motion, similar to the motion of the ripples that spread out when a stone is dropped into a pond. The wave theory explains reflection and refraction just as successfully as the ray theory. It has the additional advantage of explaining the presence of light inside the geometrical shadow, for by the wave theory, light would bend slightly into the shadow just as water waves close up behind an object floating on the water. Waves would explain it, I don't really get what I mean with rays. Reflection would also work because the light would come the same to something, and I don't know what they now mean with the ray theory. The development that disproved the corpuscular theory, so Isaac Newton's corpuscular theory with different sizes of corpuscles of light, was the demonstration in 1802 where it was disproved by the English man Thomas Young, that beams of light show interference, a characteristic of any form of wave motion. Okay, Isaac Newton said around 1680 that his idea is that wave goes in different sizes of corpuscles. Newton thought of light as a stream of small luminous particles or corpuscles with a different sort of corpuscle for each color. But when 100 years later, Thomas Young made an experiment and where he showed that light has interference. I don't know what it means, but that light has interference, and that is a characteristic of wave motion. And wave also explains why the shadow is not completely exactly there, but maybe a bit there. Some light comes also here, and some shadow also there maybe. Whatever. That was now the physics part. We're going to continue in the next part with light as waves, and the next part, light in modern physics and energy in photons. We have a complete double page. That means, if you were here for physics, you can go directly to the next part of physics. If you stay here and participate in the body center training, then it's at your own risk. We're having the leg standing hip width apart. We're going a bit down into the knees. And now flex the leg muscles and press the legs together. And now straighten one knee. Press together and flex. Straighten one knee. And bend it again, press together, flex. Other leg, bend, press together, flex. And bend it again. And now, a bit wider apart. A bit down into the knees. Flex again all the muscles and press together. And now straighten again one knee. Press together, flex. And bend the knee again. Press together, flex. Other knee, straighten it, press together, flex. And bend again. And come up. A bit closer with the legs and now press to the outside. Next exercise. One leg up, right angle with the leg, flexed foot, even lined hips, taller with the back, and press from the top against the knee. Have a little bend in the elbow. And now press from the inside. And now press with the knee up and to the side. Other knee, and press from the top. And from the side. And now press up and to the side. Next exercise, the leg up, and now press from the side and open slowly. And close again slowly. Other leg up and press from the outside and open slowly. And close it. And the next exercise, now free on the ground. First side leg on the elbow. You can do it also on the knees. And now if you like and can, one leg up. And now on the long arm. One arm out, leg up, and put elbow to knee. And now on the other side. First on the elbow. And if you like and can, one leg up. Now on the long arm. One arm out, one leg up, and put elbow to knee. And get going up again. Do walk a bit on the place. And one leg up, pull it up, point with the thumbs down, relax the leg, other leg up. Take your leg at the ankle, make a straight back, and point with the knee down to the ground. Other leg. Legs wide apart, breathe in or down. And breathe again out. One more round, breathe in. Out, breathe in and cross the legs. And breathe again out. That was for body center training. I thank you very much and until next time.